Okay, so this video is going to be all about impulse, which is just another name for change in momentum. So let's think for a second about how do we change velocity, right? Like, let's say I have a cart that's moving with a speed v, and I want to change that cart's velocity. Well, depending upon whether I want to speed it up or slow it down, I'll either push it in the same direction, that would speed it up, or if I want to slow it down, I'd push it in the opposite direction. Now, in terms of physics, what I'm actually doing is I'm applying a net force. Okay? So how do we then change momentum? Well, if I'm changing momentum, what's really changing is my velocity. So how do I change velocity? Well, I apply a net force. So what that tells me is if I want to change the momentum of an object, I need to apply a net force. So let's see what else the change in momentum might depend upon. And we're going to start with Newton's second law, the idea that net force is equal to mass times acceleration. Okay, a lot of the stuff in this unit kind of harkens back to Newton's laws, right? Like we got to conservation of momentum through Newton's third. Now we're getting at change in momentum through Newton's second. So in the second step here, I've changed acceleration to change in velocity over time. And when I multiply both sides by time, I get that m delta v that we saw up here. So that tells me that the net force times the time the force is applied is going to give me my change in momentum. And this is considered to be the impulse momentum theorem. Okay? So if I want to change the momentum of an object, I apply a force for a specific amount of time. Now you might be wondering, how does momentum change if momentum is conserved, right? And now we said we know momentum is conserved because the change in the momentum of the system is zero. So how do we change momentum if the momentum of the system is zero? Well, we're going to focus on different systems, like we did with energy. Right? Like with energy, we could have some systems where energy was conserved, but if we made that system a little bit smaller, the energy was not conserved. So we're going to do the same thing here. In a big system, the momentum might be conserved. We might have a change in momentum of zero. But in a smaller system, there might actually be a change in momentum. Okay? So let's kind of run through an example. Let's say we have two blocks, one of mass m, and I'm going to call that A, and one of mass 3m, we'll call that B, and they're going to be heading towards each other, m with a speed v and 3m with a speed 2v, and we're going to make them collide, and let's say that after the collision, we don't know how fast they're moving or in what direction. So looking at my initial system, it looks like I have more leftward momentum from block B. So I'm going to expect this system to move to the left afterwards to conserve that momentum direction or conserve that negative momentum. So if I analyze this as the A plus B system, right, I'm thinking about this. There's no friction on the surface. And when these two things collide, the forces in that collision are going to be internal. Now, of course, there's gravity and normal force, and those are definitely forces external to this AB system, but they're not in the same direction that our momentum is, so they're not going to impact that momentum at all. So if I do the AB system, I know that in this system, the change in momentum is going to be zero because there's no net force. That's considered to be a closed system. So since the change in my momentum is zero, I can go ahead and do conservation of momentum. So I have an mv plus 3m times negative 2v equals 4m because they're moving together at some unknown speed. So mv minus 6 mv for mx, 5e x, my mass cancels, negative 5/4 v is x. Okay, so that tells me that this object, negative 5/4 v, is moving to the left at 5/4, whatever v is. And since they're stuck together, that would also be the speed of the center of mass. Just a quick throwback to conservation of momentum. Now, if I was to look at the A only system, there would be a net force because there is an external force from B on A, right? If I'm looking at A only, then B is exerting an external force. So the change in momentum of system A is not going to be 0. So I can find that change in momentum, which is also called impulse. They're interchangeable, kind of like work and change in energy, by doing mass times change in velocity. So that's mass times V final minus V initial. So A has a mass of m. My final velocity was 5/4 v. I was initially moving at a positive v. So this is really 4/4 v. So negative 9/4 mv. So that's my change in momentum. Now I could take that change in momentum and set it equal to a force times time, right? Negative 9/4 mv. And if I knew, let's say, how long the collision occurred for, I could figure out the force that B exerted on A. So this would be the force B exerted on A. So it's another way of finding that kind of internal force if I don't necessarily know accelerations or things like that. So now let's take a look at the B only system. Okay. Again, if I'm looking at the B only system, the net force is not going to be 0 because there's an external force from A on B. And now Newton's third says that the force from A on B is going to be equal and opposite to the force from B on A. Right? And I just found that force from B on A. So I know the force from A on B is going to be the negative of the force I just found. So negative times negative makes it positive. So the force from A on B is 9/4 mv over t, just in the opposite direction. So I could use that to then verify the V final that I found before, to verify the negative 5/4 V for B, using the idea of impulse and momentum. That force times time is change in momentum. Okay. Well, the force that I found would be 9/4 mv over t, and that gets multiplied by t. Okay. Change in momentum is really mass times change in velocity. So we're in the B only system. B has a mass of 3m. I'm verifying V final, and my initial speed was a negative 2v. So here the t's cancel, so I got 9/4 mv, right, equals 3m v final plus 2v. So I'm going to divide both sides by 3m to get rid of that. So an m cancels, and then the 9 simplifies. So 3/4 v, v final plus 2v. So I'm going to subtract 2v from both sides. Now I get into some fun fractions, because remember, when we're combining fractions, we need common denominators. So my common denominator is going to be 4. So I got to multiply 2 by 4/4. So that gives me 8/4. 3 minus 8 is negative 5/4 v final, which is what I would expect. Hooray! Okay. Now, what you might also notice is that once we cancel the t's here, we end up seeing, or we would end up seeing, that the change in momentum of A is equal and opposite to the change in momentum of B, right? And because that fact is true, that's why the change in momentum of the AB system ends up being 0, why we could say momentum is conserved for our system, right? Because this would equal change in momentum of A plus change in momentum of B, but if they're equal and opposites, they just combine to be 0. Okay? So that's in a collision where we don't have any sort of friction or anything like that. But let's say we do have friction. I don't know how to spell friction. Friction. Okay. Well, if we have some external force like friction, like external to the system as a whole, okay, then our kind of conservation equation kind of becomes the P system initial plus any impulse or plus any change in momentum of the system is going to equal our final system momentum. P system final. And this is the impulse during the collision. Okay, so this is just before, this is just after, this is during, and this could be positive or negative, kind of like work, it could be positive or negative. So examples of negative would be friction. Some examples of positive impulse being done is if we had a tilted ramp and the force of gravity, right, might increase the momentum of our system, right? Like if our system as a whole is traveling downhill, then our center of mass speed is going to increase because of this force of gravity. So our system momentum could increase in a situation like that. So let's do kind of that similar example where we now have, M moving at V, 2M moving at 2V, but when they collide, they come to a stop. Okay. And they collide, they come to a stop. So we're going to figure out what is the impulse or what is the change in momentum of the system, because my momentum here is definitely not 0. It's definitely something greater than 0, but here my momentum is 0. So we want to figure out what is that change in momentum. So my initial system momentum is made up of the momentums of the individual objects, right, plus any impulse, and then my final system momentum is 0. So mv minus 4mv plus j equals 0. So my impulse ends up being equal to 3mv. And it's positive because the net force on the system is positive, right? Meaning in the positive direction. Not that it added momentum to the system, but it was in the positive direction. So that's the trick here, right? This means in the positive direction or negative direction, right? So our impulse here is caused by the force of friction. This block has a force of friction to the left. This block has a force of friction to the right. But since this block has more mass, it has more friction, so the overall net force on the system is to the right, so the overall impulse is to the right. Okay, so friction can have a positive impulse if our net system momentum is 0. Okay, so I can then take that impulse, keeping in mind that impulse, which is represented with the letter J, think Jimpulse. We don't ever really need to use it, but it's just fun to know. But impulse is equal to force times time, and here it's the force of friction that's causing this to change. So I can set 3mv equal to the force of friction times time. Right? I can divide both sides, and I'm going to try and figure out what the coefficient of friction is. I probably should have said that from the beginning. So I'm going to divide both sides by t. Friction is really the coefficient times the normal force. Now, what's important to remember is when I'm talking about friction, I'm talking about the system as a whole. So when I talk about normal force, I need to think about my whole system normal force. So my whole system normal force would be the force of gravity on acting on both masses, and that's the only vertical forces. So my normal force would be 3mg. Okay, so the 3's cancel, the m's cancel, I can divide by g. So there is my coefficient in terms of v, g, and t. Okay. Now, right now that seems pretty meaningless, but if we had numbers, it would make a little bit more sense. Okay. What's also important to keep in mind is how impulse can affect the speed of the center of mass. Because remember, in a collision where momentum is conserved, the center of mass speed remains the same. But in a collision like this, where we have something like friction or a force of gravity acting external to the system, our velocity of the center of mass is not going to remain the same. It's going to change, right? Like here, it was something, and then it is 0. So here, we can kind of think of our impulse equation as also being the net force on the whole system times the time that the collision is occurring equals the mass of the system times the change in velocity of the center of mass. Okay. So here, my final speed of the center of mass is going to be 0 because both objects are at rest. Okay. Remember, I can find the velocity of the center of mass by doing the system momentum times the total mass times velocity of the center of mass. So initially, my system momentum was mv minus 4mv, and I've thrown it back. So negative 3mv. And we have a total mass of 3m. So v center of mass is negative v initially, which makes sense because our system is moving to the left initially. We have more leftward momentum, so a negative velocity of center of mass makes sense. Okay, so if I was to do force of friction times time, right, I have a system mass of 3m. My final velocity for center of mass was 0 minus a negative v, and I get that my impulse or my total change in momentum of the system was 3mv, which is what we got before. So kind of two ways of figuring that out. All right, so when we talk about graphs of impulse and stuff like that, we'll talk more about how external forces can change the momentum of the system. But for now, just focus on the math behind change in momentum, which is these two equations here. All right, that's it.